Testing 1, 2. All right.
I'm reaching out across the sky, chasing shadows, learning how to fly. Every heartbeat pulls me closer now to a place where we can touch the clouds. Feel the light within.
I'm looking at this relay here. Let me see here. Let me see which page is that. This one. Okay. So this relay here is, you can get one of them for $5, 10 of them for $5. You know, your minimum purchase is one, whatever shipping is. Part number. It's a high frequency radio frequency relay. Uses a very low current to switch, which is why I'm going with it. And it can handle 30 watts at 12 volts and a quarter watt at a higher voltage. We're going to probably use it for 12 volts, 30 watts. You check the audio on this. Testing. All right, audio's good. Let me get back to what I was saying here. So it's a high frequency relay, radio frequency, radio control relay. You can get it on mouser.com. And what else I like about this? Let's get to the data sheet here. Let me present that screen. This is the data sheet screen. Contact data. Let me confirm, this is a should be a double pulse single throw. Doesn't say that here on the page, but let me see if I can find it. I mean, you can see it's double pulse single throw on the on this diagram, but let me go over the contact data. It's normally open, max switching voltage 220 volts DC or 250 volts AC at 2 amps. And that's what the contacts can handle. Coil data. The switching coil, you can give it 1.5 volts to up to 24 volts to switch it. It'll start switching at 1.5 volts. So if you want to consume low power on switching, I suggest using 2 volts or something like that. Later I'm going to try to draw out a diagram how to wire this up to switch a load with a single battery as your source, and the flyback will go back to the same single battery. So your coil versions are let's see here. 140 milliwatts, which is very low consumption on the switching coil if you give it 3 volts DC. It'll use, this is wrong with my mouse. It'll use 140 milliwatts. It'll use 140 milliwatts at 2.25 volts right here. And of course, at 9 volts, it uses 140 milliwatts. Same thing. As you add voltage, the resistance goes up. That's why it keeps the wattage rate the same. Let's go down to the schematic for this relay, which is right here. On the right here, we see pins 8, 1, 6, 3, and 5 and 4. So you would apply positive voltage from your, this is your trigger signal voltage, 1.5 to 24 volts. You put the positive voltage on pin 1 and the negative voltage on pin 8. Let me just copy this image for the making the schematic. That's the schematic for the, so you see it has pin 6 and 3 is where you're going to apply your running voltage to hit the coil. This is not your trigger voltage. This is the voltage that's going to be applied to your load, your coil. Your coil, your drive coil, which will be in series with your load on the circuit. That way, the flyback from the drive coil will power the load and go through the load in series back to the drive battery, the source, which is going to be pins 6 and 3 as well. So your source voltage hitting your drive coil is going to be connected to pin 6 and 3. And when you hit pins 8 and 1 with a trigger, it will switch the normally open contacts of pin 5 and 4 to touch pin 5 to pin 6 and pin 4 to pin 3, creating a double pole switch to pin 6 and 3, which is your 12 volts from the battery hitting the drive coil. Let's say you put you could put the positive voltage on pin 6 or the positive voltage on pin 3. It's up to you. It doesn't matter. Let's say you put the plus 12 volts on pin 6, then pin 5 will hit the plus. Pin 5 will be connected to the side of the drive coil that you want plus 12 volts to hit, and pin 4 will be connected to the side of the drive coil that you want negative 12 volts to hit. Together, double pole action, the plus and minus will connect to the drive coil simultaneously and release simultaneously. And from there, my circuit will take over and divert. This is a modification off the Bedini single pole switching method of the Bedini SG flyback system. So If anybody's in the chat, I don't know. Let me check. Ben, if you happen to show up, I'll put the link in the chat. Hold on. Where is that? There's the link. Just pop in. I'll hear it. So the let me go back to what I was saying here. Yeah, so pin 5 and 4 is where you connect your drive coil, the two ends of your drive coil to those two pins. And when this relay switches, it will connect your 12 volts from pin 6 and 3 to the drive coil in a double pole action, and it will release in a double pole action. And from there, my circuit modification of Bedini's single pole switching method will be converted to a double pole switching, so that you can now send the flyback to a single battery source instead of needing to have two batteries and swap them. You can just use one battery as your source and one battery as you're receiving the return flyback voltage after it goes through the load. So after the flyback powers the load, whatever the load don't take will go back to the source battery. Give me 1 second here to load up the schematic. The photo editor, so I can start making this schematic. Let me do that. All right. So Ben, I was going to let you use a double pole relay to do it, but I would have to, explain how to use only one side of a double pole relay, and the double pole relay that I'm using is actually more expensive than this relay, and it has a lower frequency. So with this relay, let me get back to that frequency thing. The frequency on this relay is pretty high. I think it's 900 megahertz, which is pretty high. 100 megahertz to 900 megahertz. RF data, if you see right here on the bottom left, I'll highlight it. Right there, 100 megahertz to 900. I guess it says RF data, so that's pretty high frequency. Now, you're going to need to trigger this relay with a function generator that can do those up to that frequency. If you want to use the highest frequency that this relay can handle, you need a function generator that can do 900 megahertz. If you don't have a function generator, anything that puts out 1.5 volts would do it. I'll try to find a cheap function generator online while we're doing this. Give me a second. Let me try Amazon. What would we call that? you call it? Signal generator. You don't want to search for a function generator. That's going to lead you to more expensive equipment. Just search for signal generator. All right, here's one for $10. Let me change this music. It's too gothic. Right here on Amazon, you have one for $10. I would go with it. You don't want to blow money on stuff.
The beat drops heavy like night turns to day. Feel the bass through the crowded space.
Oh, look at this. 1 hertz
Lose yourself.
triangle square output adjustable.
Euphoria's calling. Bring the fire.
Those are the there's your signals that it puts out, like the stand. This is a pretty good deal. $10.
Chase the night.
Puts out a, you know, square wave, triangle, sine wave, or yeah, square wave. So what are the specs on this? Oh damn, you have to put it together. I don't know, too much time soldering, and if you want to put it together, it's $10. Let's look for another one already built. I don't have the patience to solder this signal generator. I mean, this one for $26 looks pretty good. Let me sort by price. Five to 15 volts, and pulse frequency dual cycle adjustable. $1.50. Jeez. 200 kilohertz. You know, honestly, you're not going to need 900 megahertz unless you really want to experiment with higher frequencies. But to get this started, I would go with something like this, $2 pre-built. Let's see what else they got. It's a 555 timer. It's very common way of signal generating. Here you got 4 of them for $259. 5 to 15 volts signal. Creates a rectangular wave signal. Might as well do this. You're not going to have to really worry about protecting your signal generator from the flyback on this circuit. I'll explain later why. But you can always put a high voltage diode on the output of the signal if you're worried about it. I say get this. There's 4 pieces here, so you can, you know, you have backups in case you know, the flyback happens to burn it. You know, this one's more convenient because it's push button, and you don't have to use a little screwdriver to adjust the frequency. And this one also tells you the frequency. So I think maybe we'll go with this. That way you have more data on what you're doing when you're doing it. So let's see this one here. 3 volts to 30 volts, 1 hertz to 150 kilohertz. The relay can handle a lot more faster frequency than that, but for now you just use this. If you want to go with a higher frequency after you get it running, you can switch your signal generator after later. How's the audio coming out on this? Testing 1 2. That's good. So here you can go up to 150 kilohertz. Ralph Ring, he's a guy I like to listen to very carefully when it comes to doing electronic experiments. He says to try around 28 kilohertz. He has a lot of good results there. So with this function generator, you can do 28 kilohertz. I recommend you try that range of frequencies. Let's see if we can get the specs on this signal generator for $259. Let's see it. See more product details. There's enough information here as it is already. So here, I don't know if you could see that. Okay, you can see that. So right here where it says, where is it? Over here. That's your voltage in, V in plus, V in minus. They just give you 2 pins in case you need a backup pin. Well, you would solder your, let's say, what is the voltage on this again? 3 volts to 30 volts. So where it says voltage in, plus and minus, you're going to solder. You could use 2 AA batteries in series. Let me make sure, 3.3 volts. You know what? Just use a 9-volt battery. It'll last longer. If you want, get a rechargeable 9-volt. That way you can recharge it. And connect your 9 volts plus and minus to this point right here of the signal generator. And from there you can use these pins to adjust the frequency and the duty cycle. And that's your signal output. Ground is your negative, your minus, and PWM is pulse width modulation, is your plus signal. And it will be a 9-volt signal, I believe, because you're putting 9 volts in. Which is fine, because your relay is, what is the voltage on this? It's your relay handles. Yeah, 1.5 volts to 24 volts. So you can go anywhere from 1.5 to 24 volts to run the relay that I from Mouser here. Okay, so you would use a 9-volt battery to run that function generator to trigger this relay from Mouser. It's a $5 relay and a $3 function generator. Good shape here. This relay can handle 900 megahertz. That function generator goes up to 150 kilohertz. Plenty of range there as far as I'm concerned. So now let's get to the schematic, to drawing out this diagram to run a load or to run a drive coil, a pulse motor or whatever. And you can run a pulse motor and have it put another load in series with it. Which will run both the pulse motor and the load. You'll use the flyback from the pulse motor to run the load, and you'll use the standard forward current from you're giving the drive coil, which is going to run the pulse motor. That's standard forward voltage. This is going to drive the wheel or turn your magnetic sphere. That's in line with the electromagnetic coil to spin it. As that EM coil flies back, that flyback will power the load. And whatever the load doesn't take will land in the single source battery. The same battery that you're using to drive the coil will take the flyback in return. In a sense, you're conserving power. All right. What should we use here? Let's go with blue. Let me share screen here. All right. Let's see here. Where did I put this? All right. Let's do this one first. Oh, let me do that. This schematic to the left is the basic schematic we're going to use to arrange our diodes on a single source battery and a single coil, drive coil. Later we will place the load after the drive coil and before the source battery. So the flyback will go through the load, let's say a light bulb, and then it will go to the battery. At the same time, the coil will be driving your wheel as a standard pulse motor powered by forward voltage. And the light bulb will be powered by the flyback, the reverse voltage. Let me do something here. Scale this image down. Just need it as a reference for now. Okay. That is the schematic for the relay. I'm going to put the part number in here. I will also put the link. Might as well, huh? Put the link in here.
In the club where the lights ignite the night, beats are pumping, taking us to dizzying heights. People moving, lost in the vibrant sound. Every heartbeat syncs with the rhythms we found. Feel the bass, it's a journey we embrace. On this dance floor we lose all.
Very clear. I hope this thing, you know, it has 100 megahertz to 900 megahertz range.
Through the night we'll soar in this
I wonder if it can do below 100 megahertz, because your signal generator that we're using here is only 150 kilohertz. Let me double check that. Ben, you gaslit me for the entire weekend and last Friday till this day to get me online here to ask me for the parts. I'm sitting in your private stream while you're playing Spider-Man. So I'm just going to record this so you can use this data here. It'll probably take me another hour to get this schematic done. I've come to the conclusion that you don't have the patience to wait for me, so I'll just do it without you, and you can take your time with the schematic. And when you're done looking at it, you can you know, draw up your questions. When you figure out what you need to ask, if you need to ask anything after you're done looking at it, but I'm going to try to get everything in here. So the frequency on this relay is 100 megahertz to 900 megahertz, and the signal generator only does 150 kilohertz. I see no reason why the relay can't do a lower frequency. So it's a cheap relay. You can always test it out when you first get it and just hook the output to a continuity tester and give it, you know, 9 volts by manually touching it to the 2 pins, 8 and 1, I believe, the trigger pins. And if you get a continuity on pins 5 and 4, then it works. at a low frequency as well. And from there, you can continue building it with this relay, so you don't think you're wasting time. You know for sure you're not wasting time. RF data says anywhere from 100 megahertz to 900 megahertz. I don't think that's its limitations. I think that's its design operating frequency to perform in that range. But I'm pretty sure it can go at a lower frequency. So we're going to go ahead and keep this relay as the one we're going to use. Let me get the part number in there. The part number is manufacturer number. We'll go with this here. We'll add that screenshot to this. I wonder if I should leave the link there or not. Just leave it there, it's, in case you can't find it.
Lights are flashing, energy supreme. Riding waves of sound, lost in the dream.
There it is. We will keep this in here for reference as part of this schematic. Put it right down. All right, well, I don't know, Ben, you missed me tonight. I was waiting for you in your private chat for almost an hour. So I had to continue on trying to get this done. And it'll be here for you. And let me make this a little bigger. Once the diagram's drawn, it'll all make sense. I'll go over nicely to make sure that it makes sense. Make this a little bigger. Why is that? Oscar power partner. The image doesn't look so high resolution. Why is it such a low resolution? Windows. Come on, Windows. Capture screen already.
In the club, the rhythm moves our feet. With every bass drop, we feel the heat. Strobe lights flicker, bodies in a trance. We're lost in the music, caught in the dance.
There, that's high resolution. Okay. See if I could just put it right here. Bring it down in here. That's good. All right. What we're going to do now is make the schematic for this. So that's your signal generator. That's where your voltage goes. So we should be able to put this in the middle here. Maybe to the left a little bit. And let me see here. Let's see. Open as layer. This is going to be perfect because I can use these images to make this schematic.
Dans les rues de Toulouse, amour en fête. Les terrasses débordent de lumière secrète. Sur le pont de la Garonne, main dans la main, nous rions ensemble en ce doux matin. L'atmosphère légère comme un joli refrain.
All right, that should be enough. This is where your signal generator will get hooked up to this. Let me see if I can rotate this.
Tout le temps. Les briques roses brillent sous le soleil, chaque regard est changé, un trésor vermeil. À la place du capital saveur et couleur, je te découvre encore, tissant nos douceurs. Dans cette ville, nous vibrons cœur à cœur. Toulouse, nos âmes dansent, épris de romance. Dans les ruelles, on explore, on avance. L'amour fleurit ici comme un doux printemps sous les lumières. Pour toi je fredonne du Nougaro tout le temps. Toulouse, tu m'amuses toujours dans mes pensées. Un amour éternel que rien ne peut briser. Dans les rues de Toulouse, amour en fête. Les terrasses débordent de lumière.
Making these schematics is turning me into a professional, I guess some sort of a graphic designer. All right, let me scale that. I wonder if I gotta do that. Gotta flip this. Let's see here. Flip. Vertically. I don't like that. All right, let's just leave it like it is. You can do that later. On the left there is your minus and plus. minus on the bottom. So we'll do that. Put the coil there. Add the circuit to it. Now a single battery is going to run, you could even use 9-volt battery if you want, or you can use a larger 12-volt battery with more amp hours. So I say you do that because you want to use a single battery to run everything, even to run the signal generator. The thing is, if you do that, the flyback is going to go back to that single battery, and if the single generator is hooked up to the plus and minus of that battery to send a signal, the flyback might burn out your generator. I did not have that problem. I used this same signal generator when I did it too. I didn't have it, it didn't burn out on me. I don't remember if I put a diode on the output of it. I think I might have. So I'm just going to go ahead and do that anyway for good measure. Why not? When I put this schematic together, I'll put the high voltage flyback diode on the positive output of the oh, wait a minute, it's not going to work. I don't know. You can't really put a diode on the input of the signal generator from the source, the battery 12-volt. Unless you put it from the 12-volt positive of the battery facing the input of the signal generator. That's the only way you can put it. And that's not going to stop the flyback that's hitting the plus terminal of the battery. But you can you should be able to. No, you can't. You can't. So, you know, the reason I probably didn't have any issues burning out my function generator, even though it did burn out, that's because I was messing around with it. I probably didn't do this right. But no, it didn't burn out. It burned out because I touched the collector or something like that. You can just put a high voltage capacitor across the input on this function generator. That's the only thing you can do. And that should be fine. You can put a resistor, but it's not the current that's going to blow out this function generator. It's the high voltage from the flyback will damage it. And like I said, you need to feed power from the single source battery to the function generator and your drive coil from the same battery. That drive coil is going to fly back to that same battery. The positive flyback is going to go to the positive terminal of that battery. The positive terminal of that battery is connected to the positive input of this function generator. So is the negative terminal is connected to the negative input of this function generator, which means the positive and negative flyback will hit the input. What happened here? Testing. Testing. I guess the music is over. Okay, so the flyback will be hitting this function generator if you wire it up the way I want to. So you can't diode protect it because that would block the function generator from even receiving power to operate in the first place. The only way to diode protect the function generator is to face it towards the plus terminal of the battery, and that won't allow the power to go into the function generator, so it won't turn on. So I recommend just getting a high voltage capacitor there. A 1 kilovolt would be plenty. Ceramic capacitor. Put it across plus and minus. Not an electrolytic. A ceramic capacitor. I'll get that off the line here. And that 1 kilovolt capacitor will pick up the flyback voltage, stabilize it before it burns out the function generator. One picofarad. I would go with a higher farad rating than that. 1,000 picofarad. 1 microfarad is good. So I'll figure that out here. 1 kilovolt, 1 microfarad capacitor. One microfarad. We just put 1 kilovolt or 1 microfarad, sorry. Yeah, you could use 1 kilovolt. That'll guarantee. But I didn't use that. I used like I think it was a 35 volt higher capacitance. The capacitor is not going to blow until it goes over 35 volts, just because you hit it with 1 kilovolt flyback. There's not a lot of current there, so it takes time to fill up the capacitor. Amazon, so if you just search Google for, let's see, 1 kV, 1 microfarad capacitor. eBay, huh? So let's get back to here. eBay, let's see if we find it on eBay. eBay. Wow, never thought it'd be so difficult to find a capacitor. $1,200 volts, 0.5 micro. $7 to ship it? My God. $2 is $9. Well, you can use this for a lot of different circuits to protect your devices from flyback. Come on, StreamYard, what are you doing? Now, this is good. 1200 volts, 1 microfarad. There's no way this is not going to protect your signal generator. You would put this across the positive and minus input to power the signal generator. So we can use this image to build our schematic. Come on, man. Thank you. All right. So let's do that. Open this layer. I'm going to use this capacitor. I wonder if I should put the link in there. I'll just put the axial film capacitor. I guess I could put the link, but this link might be gone by the time you guys use it. So I'll just put the I guess the part number. What is the part number? Super Tech. No part number. Specifications, item description. Super Tech. That's the brand. I guess I'll put the eBay item number in there. That way it's easier to find. Yeah, I enjoy making these schematics too, for two reasons. So people can easily understand them and replicate them, and so I can also keep a if I want to come back to it at a later date and build it, I can without having to to redesign it or something like that. It's already done. I'll just put it down here, the image. And I'll put in the part number. eBay item number. And I'll add the specs or the details on the specs on this. Which is Super Tech 1200 volt 1 microfarad axial film. MPT, I forget what that means. Film capacitor. What was it, $4 or something? Super Tech. Oh, $9.50. $10. And shipping, $7. Well, you can search around. Maybe you can find this. Let me see. Maybe I can find another source to buy it. Super Tech axial film 1 volts 1 microfarad. Oh, that's one. MFC. MPT. See if Amazon has it. Man, it is hot and humid down here in Florida. I would have croaked already without AC. I would not be down here. I don't know how I managed all these summers. I've been here for every summer of my life. but I had AC. There was a few summers where I was struggling with the AC, but it became top priority real quick. Alright, so it looks like eBay is the only source for this. So that's what it's going to be then. eBay part numbers in there. Axial film capacitor. I'm not going to put the price. I just don't want to discourage anyone. It's about $10 for the capacitor with shipping of $7. If you want to protect your function generator, this is the way to do it. And it'll also aid in the capturing of the flyback back to the battery source. So the battery's okay at capturing flyback, but it's not the best. And you don't want to use capacitors to store any energy. You want to use the capacitor to capture the energy and send it to storage. Now, lead acid batteries are good at storing. They're not good at capturing, in my experience. They're okay. They can capture energy as well. They're just not as good as capacitors for that. All right, so the part number's in there. Let's get back to drawing this. Let's go with black. On the there. Snap to grid. Let me make sure I got everything good here. Can move this right about there. Plus, minus. Probably a little closer. Put that there. Should move this over here. Put the source here. We can do that. And put the coil here. Then move this over. All right. Ben, you still playing Spider-Man? Oh, God. Where was that? Let me see here. Oops. So the bottom one is your negative. So we got to put a battery in here. Find the image of a battery. I should already have that. Let me see. What's that? Ugh. Oh, there's my battery. Six, 4, 1. All right, we got the battery. It's going to be your single source. First off, we already know to power this, we need to power the signal generator. Right there. This part should go pretty quick. And that's going to power your signal generator. Across the battery, plus and minus, you'll put the capacitor to both protect the high voltage capacitor, to protect the signal generator, and to at the same time, you know, the battery itself should protect the signal generator. But as soon as the battery gets full, it has no room for charge, then the capacitor should take over. And even if the capacitor is charged, it should still work. You could put a neon bulb, which is 100 volts. No, you couldn't do that. What you want to do is put a I think this function generator can handle 30 volts, was it? 1 second here. Yes, 30 volts. So you could put a 24 volt automotive light bulb. They're easy to find. And you could put that across the battery, the 12 volt battery. So if the 12 volt battery ever gets fully charged, it doesn't take any more charge, then the capacitor, the 1 kilovolt capacitor, you know, it'll take the high voltage spikes, but the capacitor will never charge past 12 volts until the battery is fully charged, at which time, but you got to keep in mind the battery is also providing power to the circuit, so how is it ever going to be fully charged? But let's say for some amazing coincidence this is an over unity device and it's bringing in more power than it's using. Then the battery will get fully charged, it will have more room for charge, and it will start to fill up the capacitor past 12 volts. until it reaches 1 kilovolt. But if you put a 24 volt automotive light across the 12 volt battery, that 24 volt light will never turn on until the capacitor reaches 24 volts. And since this function generator is can handle up to 30 volts, the automotive relay, the automotive light of 24 volt light will protect both the battery from overcharging and your function generator from overcharging and blowing out. But for now, across here and here, you're going to put the capacitor. And we'll worry about adding a 24 volt light in parallel with this capacitor later. I really don't think it's necessary. Again, like I said, unless this is an over unity device, then it's necessary. But I don't think it's over unity at this stage. It might need some more work. Maybe you need it would be an over unity device if your drive coil was a superconductor. And then in which case, I'm pretty sure it would be providing more power than it takes. Actually, I'm positive it would. Okay, so that's where your capacitor goes. And I'll put that right here, 1 kV, 1 NF. Or at 1.2 kV. That's the one that we found on eBay. All right, that does that. We have your function generator powered. You can set the frequency from there and the duty cycle out to the relay to then to then switch double pole switch with a single throw instead of a double throw. The reason I use a double pole double throw is because I had 2 batteries. 2 batteries. Yeah, because I had 2 batteries and 2 coils. And, well, mainly because I had 2 coils to switch 2 coils. But perhaps the 2 battery, 2 coil circuit that I designed would be better off with a double pole single, with 2 double pole single throw relays. 1 on each battery. Because with 1 double pole double throw relay, you can't do 2 batteries, 2 coils. You can do 1 battery, 2 coil. But you can't do 2 batteries, 2 coils. If you want to do the 1 battery, 2 coil version, you can do that with a double pole double throw relay. You can also, and that would do 2 coils pulsed at the same polarity, or 1 with 1 polarity and 1 with the other polarity. It doesn't matter. You can do it either way. Or you can do double pole double throw relay pulsing a single coil in 2 polarities, switching between 2 polarities, which I also replicated that to spin a Newman type motor. You can see that on the channel with a coreless drive coil. But you can also use a double pole single throw, which is what we're going to use here. It just makes things less complicated. Plus, this relay has a much lower power consumption and It can handle more than 30 kilohertz. It can go up to 900 megahertz. This signal generator only does 150 kilohertz. So you can, the double pole, double throw relay that I'm using only does 30 kilohertz. So you have more range here with this relay. There's your capacitor across the source, and that will capture the flyback and protect the signal generator. Now we'll continue here and send plus from the signal generator to the relay. Which will go to pin 1. And minus will go to pin 8. And there you have that. That's your connection for the signal generator. And that will send a signal to the relay and switch it at whatever frequency you set it to, from 0 hertz to 150 kilohertz when using this particular signal generator. You can always use a different one that can do up to 900. So this relay, what is the name, the model number of this relay? TE Connect Axicom. It's made by Axicom. This relay by Axicom can handle 900 megahertz. So it's a radio frequency. It's designed for radio frequency. RF. TE Connectivity, manufacturer, TE Connectivity Axicom. Let me just put that in there. Manufacturer number. TE. Put it down here, oops. Almost done, believe it or not. Once I get down to putting these diodes in there, then I'll go over the circuit and how it will operate, how it should operate. Of course, this is not replicated, but I am an electronics engineer, a degreed electronics engineer, and based on my knowledge, it should operate. Put the part number in here. Man, I wish I knew how to do that. Okay, so I'm gonna put the part number manually. Again, it's too lazy here. 146-2043-8. You can find it on mouser.com. And put the Mouser number also, 655-146-2043-8. You can use this number to find it on mouser.com a lot quicker. 655146. Okay. I'm getting used to talking to myself, I'm telling you. Eventually someone's going to listen to this and get something out of it. Hexacom 46. Oh, sweet. Yeah, that's good. Merge visible laser. Okay. All right, now we're going to draw in this guy right here. This. So let's put the coil in first. The coil, where's the coil? Oh man, I already had an image of the capacitor. You could put a resistor on the input of the function generator on the plus side to limit the current. Or you can use a potentiometer, and that will help you further tune your how you energize the coil. You know, you'll be sending the same 12 volts. Is it 12 volts? Yeah, 12 volts to the signal generator, which will then trigger the relay, and you're going to give the relay the same 12 volts. But if you add a potentiometer to the input of the signal generator, you can also vary the resistance. But you know what? That's already done with the duty cycle. Well, you could put the potentiometer on the relay side, plus the plus portion going to the coil from the source, and use that potentiometer to vary the current hitting the coil to add more dynamics to how that coil is pulsed. The voltage won't change, but the current will. So if your coil is, let's say it's a 24 ohm coil, and you feel like it's pulling too much current to run your load, you can turn up the resistance to that coil. You know, but your load also has built-in resistance, so the coil, even though it draws power, if your load is in series, it will add to that resistance. There's all kinds of things you can do to mess around with these circuits. So here's the drive coil. That's a horrible image. I'm going to find another image of a coil. This one is just... Uh-oh. Are we freezing? Come on now. I don't know what happened there. A little freeze action going on. Perhaps the Russians are hacking me. Feel free. So we got a coil here. Let's get a nice image of a coil, an inductor. It's 11 p.m. already. Jeez. So this coil will represent your vortex coil, Ben. That means you can use this coil to represent your vortex coil in your vortex coil. Let me just find a nice image of our coil here. Yeah. Let's go with this one. Okay, there's layers. This will be the drive coil. Pins 6 and 3 is where you want to apply. You want to apply the battery, plus and minus. So we'll take the plus here. Let me figure this out first, because we're going to put the load in series. And go back to the battery from there. So put your battery voltage on 6 and 3. 5 and 4 hit the coil. Right, we can do it like that. All right, let's leave it right where it is. Then flyback will go through the load, the light bulb, back to the battery. Let's try this out. So you're positive from the battery. Let's delete that part of the image. It's in the way. Don't really need it. What on earth are you doing? We can do it like that. That would be your plus. There's just so many ways to do things in electronics. So many different parts you can use. I'm picking out the cheapest part I can find with the most capabilities and the lowest power consumption, and within range of the specs of the circuit needs. So the relay can handle I think it was 60 watts at 12 volts. Let me check it here. Rated current 2 amps. So 60 watts. It has a switching voltage range from the max switching voltage is 220 volts DC, so you can go anywhere from 1 to 220 volts DC, and anywhere from 1 to 250 volts AC, but the current they can handle from within that voltage range is 2 amps. So if you're two amps continuous current. So let's see here, contact data. It can do 30 volts DC at 2 amps. And 110 volts DC at 0.3 amps. So it can do 33 watts at 110 volts DC. It can do 60 watts at 220 volts DC. I don't know how that's possible. Whatever. It's, you know, 30 to 60 watts depending on what your voltage is. But if you're using, I say 60 watts is the most this relay can power. I don't advise you using it at 60 watts. I would run a 30 watt load with it to be on the safe side. Whatever your light bulb is, if it's a 30 watt light bulb, that's good. When it comes to LEDs, that's awfully bright for a 30 watt. You know, 30 watts is more than we're using, most of us, with these pulse motors and stuff like that. You can stretch it to 60 watts, but I would not keep it at 60 watts long term. I would run this relay 30 watts continuous, 12 volts on the hitting the load coil. So if your load coil is has 50 ohms, or let's say it's a 100 ohm drive coil, and you're giving it 12 volts, let's figure out the wattage for that. What is the wattage that coil is going to consume? So V over IR, so voltage 12 volts divided by, what is wrong with this? 12 volts divided by your R. V divided by R is your I. R is your resistance, I is your current. So if it's 100 ohms, so 12 divided by 100 is a 0.12 current, amp, I. So that's 120 milliamps. So you take that 0.12 and you multiply it by 12 to get your watts. So you multiply 0.12 times 12. It tells you the wattage that coil will consume. And that's a 1.4 watts. So that sounds about right, up for 100 ohms on a coil. But your coil is probably around about 20 to 25 ohms. So 12 divided by, let's say, 20 is 600 milliamps, which sounds about right. That sounds about, the Bedini's drive coil was like 12 ohms, and the trigger coil was 24 ohms, somewhere around there. So let's do that. 12 divided by 12. Well, actually, let's go with 15 on the drive coil for ohms, and let's go with 28 to 30 ohms on the trigger, because that's what I remember. So 12 volts divided by 15, which is V divided by R. 12 volts divided by 15 ohms is 800 milliamps, which is right about what the Bedini coil would consume. So you take 0.8 amps and multiply it by 12, and you get your wattage, and that's 9.6 watts. This relay can handle that wattage all day long. So whatever you add in series with the Bedini drive, with a 15 ohm drive coil, you want to do the same thing. So if you're adding a light bulb, a coil, a light bulb that has, you look at the specs of the light bulb, it'll tell you the wattage it consumes. So you got 10 ohms on your drive coil to produce the flyback, and you have another 20 watts left over. I'm sorry, you have 10 watts basically being consumed by your drive coil. If it's a 15 ohm coil and you're giving it 12 volts, that's about 10 watts consumption. And you have another 20 watts left over to run your light bulb in series with the drive coil. And the drive coil will consume the forward power, and the light bulb will consume the flyback. And whatever the light bulb doesn't consume, the light bulb will be in series with the flyback and the source, positive terminal of the source. I'll explain how that works in a bit. Let's see. How's the Spider-Man been? All them video games. I gotta ask you, where do you get these games? It's a lot of games, man. Are they free? I can't imagine buying them all. That's a lot of money in games. So we got your positive from the source hitting pin 6. We're gonna run the negative to hit pin 3. Oh my God. The chicken's been baking for over 2 hours. Oh my God. Still good. Whew. Well done. All right. Holy, forgot to turn the oven here. Thanks for letting me know, Mikey. Mikey's the name they gave the dog I adopted at the pound. They gave him my name. He's always concerned about food. Hey, stop that. Stop. Cut that out. So, the negative from the source. Let's see. It is hot. If you guys ain't seen that movie, Disclosure Day, it was good. I liked it. All right, that's where your source voltage goes. And from there, the pins 5 and 6, 6 and 3. Sorry. So 6 is your pin. 6 is your plus, and pin 3 is your minus. We'll put the plus and minus sign here. It's hard to get that nice, but there it is. So that plus and minus is your source polarity. We do one more thing here. Make this plus a red. And we're going to send pins 5 plus to the drive coil. Now this looks complicated, but it's really not. Once you understand the concept here of generating flyback on an inductor and using that flyback to do work, and it could power a light bulb flyback. I don't know if it's how good it is at powering you know, like a high amperage load. That requires stepping down the high voltage with a step down transformer to a lower voltage, thereby increasing your amperage for that high amperage load. That's how I would do that, but you can use the flyback pretty efficiently to power light sources, you know. I guess I can do it like this. And then you would do it like that. So that makes sense to me. And this is how this relay is going to switch this inductor. And you can use that inductance going to that coil in two ways. One, you could use it to drive a motor. You could use it to generate sound, a lot of ways, but this is the two main ways. You could use it to consume the forward energy, the forward polarity plus and minus pulse from the battery, to drive a motor or do work in that way. And when it rebounds and flies back, you can also use the flyback to power a light bulb, or you can step down that flyback to also power a higher amperage device. There's a lot you can do. This is just experimental design here. You can add to this in many ways. This is the fundamental setup. So now that you're inducing this coil, you're going to run your diodes. Now looking at this reference schematic here with the double pole switching, we're going to add the diodes like that. So you can see over here, the plus hits one side of the coil with the switch, and then this plus over here shifts over to this side and gets funneled back this way to the battery. I don't really need this reference. I've got this pretty much locked down. So we're going to put our plus is going to hit this side of the battery, but the flyback plus will be on this side. So we'll put our flyback diode here. And send it back to the battery. After the load. So I'll put a light here. And let's add the light symbol. I think it's in screenshots. Where is that? Okay. I gotta find the light symbol. Oh, there it is. What is that? 4446. All right. This is the symbol for a light. Almost done. Okay. Is this right? Yeah, do that. Right. All right, so there's your light. And I'll explain this operation in a little bit. Let me finish drawing this. And then we're going to run this circuit back to the bottom side of the light. Here is the positive flyback side of the coil. So we'll run this other end of the light. The positive flyback will go through the light to the positive terminal of the battery. And the positive flyback will cut through the light and the positive terminal of the battery over to the negative terminal to reach the negative flyback. Okay? And that's how that works. Rewind that and repeat what I just said. I'll say it one more time. The positive flyback will cut through the light over to the positive terminal of the battery, through the battery to the negative terminal where the negative flyback will be connected. This way the flyback's positive will meet with the negative and complete the circuit so that the flyback can actually be consumed through the light and the battery. In other words, the light and the battery will be the load, will be in series with each other, acting as a load for the flyback. So I'm not like a seasoned experimenter. I mean, I experiment on my own a little bit here and there. I'm not like an esoteric, experimenter, but I've done some experiments. For many years, I replicated the Bedini SG on my own and figured out its operation and completion. I have a degree from ITT back from 1997. I've been working in high voltage since 94. I'm 53 now, so it's been a good 40 years working with electricity. I've been shocked hundreds of times. I think by now I kind of have a good understanding how this voltage and current are working constructively and destructively. I think I've both destroyed my body with high voltage shocks as well as healed it with high voltage, low current pulses, which I was, when I got that Bedini pulse generator working, I was holding on to the terminals, squeezing them harder, and I would get that pulse to reach my feet the harder I squeezed. I think that was healing because it didn't feel like it was hurting me in any way, you know? It might scare anybody else, but me, I'm used to getting shocked by high current, and 100 or 200 volts. I've been shocked by 400 volts once. Thank God it was only once. I've been shocked by 110 volts, 120 volts, hundreds of times. I've been fortunate enough never to be hit by 220, but I kind of know how it feels because I've had it described to me by electricians in the field who have been hit by 220. And I know what it feels to get hit by 440 or 480 volts. And man, that was so brief, but that really damaged my shoulders for 6 months. The power went in my pinky through both shoulders and out the other hand to ground. All right, let me finish this. So the positive flyback, which is right here on the coil. I'll go over this after I'm done drawing it. Yeah, goes right here. That is the same point that hits the positive of the battery. And that should be fine. And now the negative flyback is over here. So this is easy. It's funny, I've been doing this stuff for years, and I never, in school, in ITT, they taught us about the flyback in a different way. They didn't call it flyback. I'll go over how they taught me the flyback at ITT in a little bit. And how I understand it. They taught it to me more of how you would explain pressure moving from one side to the other. So right now I'm sending the negative flyback to the negative of the battery. And you got your 1.2 kilovolt, 1 microfarad capacitor across the battery to protect sensitive electronics from the flyback and to double as a more efficient way to capture the flyback and send it to storage. To assist the storage device in storing the flyback and capturing it, especially at high frequencies. When you turn up the frequency, the battery might not capture the flyback at those frequencies. It'll capture some of the pulses, but not all of them. Let me erase this now. Don't need it anymore. And that's that. And we're going to put the diode in. I'm not sure if this requires 2 diodes or 1. I'm thinking right now at this point, I'm thinking might only need 1. We'll find out. That is the circuit. Now, that shouldn't be a problem. That would be your positive flyback diode. Jeez, I messed up here. What is going on here? What? Oh, that's what it is. All right. All right. Thinking I only need one flyback diode here. Oh, wait a minute. Okay. Can't even do that. Oof. Put the diode in the wrong place. Can't put the diode there because you'll block the source from feeding the relay. This source plus from the battery has to feed this relay. Gotta move it over to somewhere else. I'll show you in a second. It has to be, you have to let this power get to the this point. So you can put the flyback diode. No, you can put it over here after the light. That's a better place for it. That's where you want it. That way you don't block the power from getting to the relay. And the flyback will be forced to go back to the battery. The capacitor will protect the flyback from absorbing into the electronics there. And it will funnel it into the battery. Okay, let me see. Do I need another diode like I usually use? We have to route. We already routed the negative flyback channel back to the battery. It's right there. So that negative flyback will hit the battery. Let me start to go over this operation here. Let me first double check something. Negative flyback will go over here, back to the battery and the capacitor, which is fine. I don't see any problem with that. Oh, I see what I did. That's why I need the other diode. So, yeah, in actuality, this point is connected. I don't know why I took it out. So I got to put it back in. This actually does need to be connected here. All right. And we will put connection dot there to make that clear. So all that is connected there. And now I will explain, let me see here. Negative flyback. I'll put in the flyback polarity in green on the coil. Okay. So you can see how the plus goes through the light back to the battery. And your high voltage diode is right here. I'll keep it in green so it represents the flyback. What is going on here? Give me a break. Let me just redo this. Okay. Let's see what we got here. So the flyback polarity is in green. You've got your plus cutting through the light here. And the diode keeps it going this direction over to the plus of the battery. Of course, the flyback will hit this signal generator, but this capacitor here should protect it. It's been my experience. Do I need a negative flyback diode? So here's the negative. Let's trace it. Negative flyback. And it hits here. And then it goes over to here. Which doesn't do anything. It's strange because I needed it before on other designs. I think I still do need it. I'm trying to find it. Where was it? It was canceled on the line. Ah, there it is. Is that it? No. That's not it. I don't know why here I don't seem to need it, but I needed it on other circuits. That is strange. That is super strange. Let me bring up that image again. There it is. So in this image, we have the positives from the battery hitting here, sending positive flyback here, negative flyback here. And the positive flyback would go to the negative of the battery. It looks like you don't need the negative diode, negative flyback diode here either. I don't know why I put it there. Hey, we all make mistakes, huh? I mean, this is the negative flyback diode. Right here. What's it doing? Oh, that's why. Because when you send positive from the battery over to here, you're just going to short out to the battery. So, let me go back to here and find that. So positive from the battery right here goes here, and it also goes over here. Well, it stops here because of the blocking diode, but it ends up here. And when the switches are closed, when these switches close, that's when the problem occurs. And when these switches close, this positive from the battery will be able to go through here, over to here, to the negative. That's why you need the negative flyback diode. I almost forgot. So you need the negative flyback diode to block the positive from the source. All right, I'm going to add that diode now and explain it later in a bit. So the negative flyback diode needs to be here, because you don't want to short the positive to the negative. You put it there. Believe me, I've replicated this. This works fine. You don't need two batteries to do you don't need to swap batteries like the Bedini SG circuit. You can do the Bedini method with one battery, capturing the flyback. You don't need to swap anything. But with Bedini circuit, he has different reasons for swapping the batteries. I don't agree with him. I've actually demonstrated the flyback actually going back to the source battery with voltage differentials and seen it go back. So I've seen it go work the Bedini way too, but he was single pole switching. With this double pole switching, you can do it with one battery. So now we have the negative flyback diode in there. Let me put the diode number in here. What on earth are you doing? What did I press for it to do that? I don't know. One more time. All right, there's your flyback diode on the negative side. And that will pass the negative of flyback. I'll explain in a second. Okay, so now that diode there serves a very important purpose. If you don't have it there, when the switch is closed, you're going to short out the positive terminal of the battery to the negative. And I'll show that right now. This positive terminal battery will go over to here. Take that off. It'll go this way. The positive of the battery will go from here. When the switches close, both of them close now. The positive will channel this way over to here. If this diode is not there, the positive will go this way, hit the negative of the battery. And that obviously wastes power and makes it so that your drive coil doesn't even receive charge. So now that you have the diode there, you're blocking that from happening. That's why it needs to be there. All right, so we're done here with this circuit. Now I'm going to go over the operation. This is a double pole single throw radio frequency relay capable of doing up to 900 megahertz. It could take 1.5 volts to 220 volts DC. No, 1.5 volts to 30 volts on the, let me double check that, I forgot already. It takes, yeah, the switching coil inside the relay can handle 1.5 to 24 volts. So we're going to give it 12 volts from a 12 volt source. And it can do 30 volts at 2 amps, 60 watts on the relay contacts. It can handle 900 megahertz. We're using a signal generator that can do 120 kilohertz and handle 3 volts to 30 volts. And we're going to give the signal generator 12 volts. Okay, going over this circuit now. You're going to give 12 volts positive here and 12 volts negative here to the signal generator to power it. From there, you're going to adjust your duty cycle and frequency. And it's going to switch a 12 volt signal to the relay. Right here, your negative will go here, and your positive signal, 12 volt signal, will go there. You can vary the duty cycle and frequency with the signal generator. From there, you're switching, your double pole switching an inductor. You're going to send plus 12 volts to this side of the inductor and minus over here, indicating the right here your polarity of the inductance polarity to the inductor. And you could drive your wheel during that phase of the operation here. Of when you induce this coil, you want to use that power to drive a wheel or do something. And after you're done driving the wheel, the coil will fly back with this polarity here. And the flyback will be utilized to run a light. Here's your light. So your plus flyback will go through the light, through the flyback diode, forcing it over to the positive terminal of the battery. It'll cut through the positive terminal, out the negative, through this diode, back to the negative of the flyback, which is over here. All right, so that's the cycle of the flyback going through the load and the battery quite effectively, as far as I can tell. If you want to use the flyback to power something other than a light that requires more amperage at a lower voltage, you can use as a step-down transformer. And basically you would put the transformer here. And your high voltage would get stepped down with a coil. To a low, how do I put this? You would put a primary winding here with a high voltage number of turns, with a lot of turns to pick up the high voltage. And this is an isolation transformer, so your secondary would have fewer turns. And you would send the positive here and the negative over to here to run a lower voltage, higher current device. I think that's how Gerard Morin did it with that washing machine motor, because that washing machine motor has a high voltage coil I know it's a step down transformer in there, or step up, or something like that's going on. But I think that motor has the isolation transformer that's very well designed to do this. But yeah, for now we're just gonna leave it with a light. All right, it's midnight. So I'll go over this one more time. The positive of the battery feeds to the function generator. The negative of the battery feeds the function generator. This switch here, positive and negative. I didn't do this part. The positive of the battery connects over here, and the negative of the battery connects over here to send that battery voltage to your coil, your drive coil, via the double pole switches right here. And when these two close together, they ignite this coil, and then they open together, and the coil flies back with this polarity. And that flyback cuts through the light, through this diode, and hits the positive terminal of the battery right here. Goes through there, out the negative, through this diode, back to the negative side of the flyback. I'll post this later, this circuit later on a quick video. Everything looks good here to me. Hope you guys enjoyed that. Yeah. Over now, guys. Have a good evening. I'm burnt. Talk to you later, guys. Let me see. Do it now! Come on. Do it. Get to the chopper.
Come on. Do it. Do it. Do it.
Where is that? Ah, there it is.
Get to the chopper! Get to the chopper! Come on. Do it. 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 Who is doing it? Do it. Do it.
Testing.
All of it. Do it. Come on! Do it now! And I would do the rest.
Are you kidding me? My mic was muted this whole time? Testing. Why did it say my mic was muted? Oh, okay, we're good. All right, one more time. Get to the chopper.